Hello, I'm Tom Stanley of Hendrix College and Deakin University. Today I wish to show how to calculate the weighted average of the adequately powered, or WAP, and the median power of an area of research. In a couple of recent papers, we show how WAP reduces publication bias if some researchers select for statistical significance at little loss if there is no publication bias. Both papers are published with John Ioannidis from Stanford and Chris Dukougliakis from Deakin University. Before any calculation can be made, we must have collected all reported effects from a given area of research. For example, say the effectiveness of some new drug or the effects of raising minimum wage on employment, and all of their standard errors. This is exactly what any meta-analysis requires. Next, we calculate the unrestricted weighted least squares, WLS, weighted average of all these estimated effects, and we use this as a proxy for true effects, or more precisely for the mean of the distribution of true effects. In two different recent papers, we show that weighted least squares weighted average has less bias than random effects when there is publication bias, but is as good as random effects if there is no selection for statistical significance. WLS uses optimal inverse variance weights, but unlike the fixed effects, WLS automatically adjusts its standard error and its confidence intervals for any heterogeneity when it's present in the research record. WLS is calculated from the simplest possible regression, where the t-value, which is the effect size divided by its standard error, is the dependent variable, and 1 over the standard error is the independent variable. Estimates of gamma here is the weighted least squares weighted average. Notice that there's no constant or intercept into this regression. Any regression package will automatically calculate the estimated slope, which is the weighted least squares, and also calculate its standard errors and its confidence intervals. Once we have a proxy for the mean of the true effect size, which is this WLS, we are ready to identify retrospectively which studies have adequate power, that is, which studies have 80% or higher power. For decades following Cohen, adequate power has long been arbitrarily and conventionally defined as 80%. In order to achieve a statistical power of 80%, true effect, which again we estimate by WLS, must be placed such that 80% of its area falls within the rejection region, which is to the right of the conventional 1.96 critical value that you look up in a standard normal distribution. And the curves look like this. This should be very familiar to everybody. We start off with the null hypothesis, assuming the effect is equal to 0. You look up to 95%, you find a critical value of 196, and then everything to the right of 196 will be in the rejection region. That's all pretty straightforward. What you might not have remembered is it turns out that if the true value is exactly 2.80 standard deviations to the right, that will give us exactly 80% of the curve in the rejection region that is to the right of 196. How did I get that? Well, very simple. You simply take the 1.96, you subtract the 2.8 from that. Of course, that gives you a negative 0.84. You look up a negative 0.84 in the normal distribution, and you find a probability of 0.2995. And you add that to half of the distribution. Half the distribution is 0.5000. You take the 2.995, add it to 0.5000. That gives you 79.95, and that is approximately your 80%. So that's where the 80% comes from. The big lesson here is that this number 2.80 is important, and it turns out then, as long as the standardized true effect, which we calculate by this weighted least squares estimate divided by standard error, is greater than or equal to 2.80, we have something that has 80% or greater power and hence is adequately powered. Playing around with this inequality just a little bit and solving for the standard error, this inequality means if the standard error is less than or equal to this weighted least squares divided by 2.8, just quick rearranging, that means that power will be at least 80%. So this is basically the lesson in how we identify whether or not an estimate or a study is adequately powered. If its standard error is less than or equal to the weighted least squares divided by 2.8, we're in good order. We have an adequately powered study. Okay, now to find WAP, we go back to all of our effects and their standard errors and sort them from low to high and retain only those where the standard error again is less than WLS divided by 2.8. That is, we only keep those which are adequately powered. And then again, we run a simple regression on just that subset of adequately powered studies in order to get an estimate of gamma, which is going to be now our WAP. When we use all studies, this estimate is the weighted least squares. When we just use the ones that have 80% power or more, it becomes the WAP. And that's really all there is to it. That gives us the weighted average of the adequately powered. Lastly, our large survey of economics research has reaffirmed the importance of power. Thus, we recommend that all meta-analysis report the median power that they find in their particular area of research that they investigate. To do so, meta-analysis can either use this weighted least squares, weighted average, or the WAP, either one, as their true effect, and then simply standardize it by dividing it by the standard error of the typical study. That is, we want to divide it by the median standard error that we find in a particular area of research. Once we do that, we can now figure out what the median power is very simply. Suppose, for the sake of argument, in a particular area of research, the weighted least squares happens to be exactly twice the median standard error for that area of research. And so now our curve, which before, under the alternative hypothesis, was at 2.8, suppose now the true effect gives us a standard standardized effect size of 2.00 exactly. Suppose that happens, okay? And again, we get this by simply taking the weighted least squares, dividing it by the median standard error, okay? That's how we got to 2.0. Okay, so now again, we simply want to calculate the area to the right of 196 as we did before. The process is exactly the same. It's just where we center the distribution is different because we're looking at a particular average value of precision, which is going to give us the average value of our power, the median power. So in any case, it's a very simple calculation. Again, we take our 196 as we did before. We subtract the 2 from it because that's where the center of the new distribution is. We now get a calculation of a minus 0.04. We look that up in a normal distribution. When we look that up in a normal distribution, we find a probability of 0.0156 is the area in between those two. But power is anything to the right of 196. So again, we have to add it to the whole right half of the curve. When we add those two numbers together, we get 5156 and make a percent out of that. So the median power would be almost 52%, 51.56. Just to take quickly another example, suppose in another area of research, we have the weighted least squares is exactly equal to the standard error that we find in the average study, the median standard error. Suppose those two things are exactly equal. So in this next case, they're equal to exactly 1. To do that would mess up my distribution pretty badly, but I'm moving the curve further to the left. When you do that, you do the same kind of calculation. You take the 1.96, you subtract 1 from that, and that, of course, gives you 0.96. No hard arithmetic there. That's a z-value. You look that up in a normal table. The probability you get when you look up 0.96 in a normal table is 0.3315. But now, because the curve is in between 0 and 196, we have to take this 0.3315, and we have to subtract it from 0.50. We subtract it and we get 1685, 0.1685, or roughly 17% is going to be our median power. Those are two examples how you get median power. I hope this has helped you a little bit. Thank you very much for your attention.